All right, so the next titration, of course, would be the weak base strong acid titration. Same basic idea as the weak acid strong base, same basic idea as the strong base strong acid titration, kind of a combination of the two. We will be dealing with buffer solutions, so Henderson Hasselbach again in stage 2, only in a slightly different angle. You shall see. But it starts off the same way. We're going to have a base with nothing added to it, no acid yet. So calculations have already been done on here. And we know that the concentration we're starting with, according to the example on your sheet there, is that it's 3.75 moles per liter of ammonia, which is also ammonium hydroxide. What we can't do is find the pH of that because we have to go through the dissolving of the weak base ammonia. So let's take a look at that. This is what's happening here. NH3, which is ammonia, is a Bronsted-Lowry base. Why is that a Bronsted-Lowry base? Because there's no hydroxide on there. We need to turn it into an Arrhenius base, which does have hydroxide, by adding water or, of course, HOH. Single displacement reaction. Well, actually, this is going to be just the hydrogen attracted to the nitrogen, and the OH following along for the right. So we just simply add HOH, an additional hydrogen to the NH3, and then add OH to the end of it. That is now a weak base, which will hydrolyze, will break apart, in NH4 positive plus OH negative. Now the Kb for that is 1.8 times 10 to the negative fifth. So when we find the dissolving of ammonium hydroxide, we're going to get OH negative in the products, which means it's going to be a basic solution. So it'll start off high, which is what we expect it to do. I won't bore you with the mathematics. You can follow along if you want, but we should end up with a concentration here of 3.67 times 10 to the negative 3 moles per liter. So that's going to be the second one we put in here, 3.67 times 10 to the negative 3 moles per liter of hydroxide. And when we find the pH for that, we simply take 14 plus the log of that. And we get 11.56 with my 2 decimal places. So we're going to start off high, not as high. If that had been a pure strong acid, it'd be very close to 14, somewhere between 13 and 14, but it's dropped almost 2 full points from that because it is weak, which is what we expect. Now, in the weak acid strong base titration, we saw a big jump. In this case, we're going to get a big dip because it's doing exactly the opposite. They're kind of inverse relationships. Okay, so now that's stage 1 right there. Now we're going to have stage 2 for these 3 parts right here, because we have a mixture of weak base and strong acid, and in all the cases the amount of weak base is greater than the strong acid. And so if we take a look at the stage 2 of that, like I said, the differences in the number of moles, it's going to create a buffer, because what you're going to do is you're going to create, here's your reaction right here, the weak base and the strong acid, double displacement reaction, gives you the weak acid, which is the conjugate of ammonium hydroxide, plus water. Now, what's going to happen now is that we have to have the we have the Kb established with 1.8 times 10 to negative 7, or negative 5 rather. So we're going to continue with that for now. So we get to this right here, we got 0.045 moles of NH4OH, and the first one we have for the HBR here that's not 0 is 0.015 liters, which is 0.0118 moles of acid. So we're going to put 0.0118. And of course, there's none over here, but that'll change momentarily. We're going to lose all of this, subtract 0.0118, and we're going to gain 0.0118 over here. Now this is weak acid. This is going to give us weak base, 0.0332 moles of weak base. So now we have a buffer. Okay, so the buffer here, we have to divide both of these by the total volume. So we go back over here and find the total volume. For this is 0.075 liters. So we divide both of those by 0.075 liters. Okay, so 0.0332 divided by 0.075 liters. This is 0.443 moles per liter of weak base. And for the acid, this one is 0.157. So 443 and 157 then go over to our concentration. We'll first put the 0.0332 and the 0.0118 in for our excess, 0.0332 and 0.0118. And let's make sure we got acid and base figured out here correctly. So yeah, base is the 0.0332. So that's weak base, and this is weak acid. Okay, so then we divide them by 0.075, and we got 0.443 moles per liter of weak base, and we got 0.157 moles per liter of weak acid. So now we got to go to Henderson Hasselbach, since this is a buffer. All right, so Henderson Hasselbach pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. And right here we see an issue. The issue is the fact that we want Ka, not Kb. So we got to change Kb to Ka. So 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5th gives us 5.56 times 10 to the negative 10. So that's the value we're going to put in right here. So the pH is equal to negative log 5.56 times 10 to the negative 10 plus the log of the concentration of the base, which is 0.443 over the acid, 0.157. Punch that into your calculators. Negative log 5.56 E negative 10 plus the log of 0.443 over 0.157, and you get a silly number. Hang on, I've got the parentheses after the negative 10. Let me fix that. Insert parentheses. And we'll get 9.71. So we'll go back to the chart. and put in 9.71 right here. So a big drop, almost 2 full points, kind of like the big rise of quite a bit in the previous problem that we did in the last lesson. Okay, so now we come over here to the 0.0225 for the acid for the next scenario, and this is where we get our half equivalency. We got 0.045 moles of the weak acid, 0.0225 moles of the weak base, plus 0.0225 moles of the strong acid. We lose all of that. We lose 0.0225 here. And we gain 0.0225 here. And give us 0.0225 moles of the weak acid and 0.0225 moles of the weak base. So we plug that into Henderson Hasselbach. pH is equal to negative log of 5.56 times 10 to the negative 10 plus the log of, well, we're going to divide these by the total volume. So let's go over here. It's 0.09 liter. Oh, we probably should put those in there, shouldn't we? We'll come back and do this over. 0.09. So divide by 0.09 liters here, divide by 0.09 liters here, and you get oh my goodness, you have 0.25. Yeah, 0.25 for each, yeah. So we get 0.25 moles per liter for each. All right, so we'll put 0.25 moles per liter here, 0.25 moles per liter here. And we know we don't even have to calculate that at all because it cancels out. So we just take the negative log of 5.56 times 10 to the negative 10. So let me get my bookkeeping done first before I start doing that. So we got 0.0225 of the weak base, 0.0225 of the weak acid. This is 0.25 more weak base, and this is 0.25 more weak acid. And then I just take the negative log of 5.56 times 10 to the negative 10. And I get 9.25. So, of course, the drop kind of levels out. Only a drop of 0.46 there.